Hi, everybody. Thank you so much for coming. So my name is Victoria Levy, and I'm a senior FinOps engineer at Alteryx. And today I will walk you through a gentle introduction to using data science and analytics for FinOps. And so on the agenda today, I'll go through how to create a model, and we'll go through the steps one by one so you can get an idea of what goes into that. And I'll talk a little bit about what my team is doing today for data science and integrating that with FinOps. And then at the end, I'll share some tips as well as some caveats for implementing this in your own FinOps practice. All right, but first, a little bit about me. So, there we go. So I've been in the FinOps space for about 4 years now, across a handful of companies, and like a lot of FinOps practitioners, I didn't have a direct path to get there. So I'm originally from New York, but I moved to Austin to study physics at the University of Texas. And so the natural next step for a shy physicist was to go straight into a frontline sales role. So I eventually moved over to a more technical role, but it was through that sales role that I got enough interest in business that I went back and got my MBA. And then after doing FinOps for another couple more years, I came to Alteryx, which is a data analytics software company. And that changed my perspective once again to where now data science is front and center to what I do for FinOps. All right, so why use data analysis for FinOps? Well, let's take a step back to my physics experience for a little bit. So when I was going to classes, there was a sign that we passed in the hallway every day, and that sign said, "Is the why keeping you up at night?" And that really stuck with me to where every time I encountered a new problem, I wanted to dig deeper into the why behind some of the decisions we were making. And so you'll see this come up as a theme throughout this talk. And let's see. Oh yeah, and so as FinOps practitioners, we look at data every single day. And so to me, it felt like data analysis was an undertapped area for FinOps. And so I really wanted to bring that front and center. And our job isn't just about getting cost optimizations, it's also about bringing business value. And so we can do that through deeper insights into our data. And for me, my goal is to help create some better forecasts as well as get those deeper insights. All right, so some of the data that I look at on a daily basis are those forecasts that come out of our tools. So I call these out-of-the-box forecasts. And some tools might be able to pick out the patterns in your data, but they don't really know your environment like you do. And so I challenge you to see if you can answer some of these questions, like, can you explain why this is the forecast that the tool picked? Can you justify this forecast to your stakeholders? And how confident can you be in the estimates that it provides? But now, if you build your own model, you actually gain the ability to tune those forecasts based on what you know about the business. And, nope, there we go. And you'll actually be able to customize some of the parameters based on what you know. You can adjust those forecasts to get improved accuracy over time, which is not something that you can always do with these tools. And then if you get really fancy with the statistics, you'll be able to estimate a range of forecasted values so that you can even do some risk analysis, whether your forecast falls at the top of the range or the bottom of the range. And we're on the next slide anyway. So now this is another why question, and this one might sound obvious, but what is forecasting? Why do we forecast? Well, forecasting helps us make decisions today based on what we think will happen in the future. And so this is similar to planning, but a little bit different, because with planning, you're kind of listing out what you think you'll spend, but we're actually going to look at it from a statistics perspective and map out some of those patterns. So theoretically, a better forecast should lead to better decision-making as well as better planning. And so our goal isn't to get an exact number, but we want to get somewhere in the range of where a good forecast is. And I have a bit of an example as well. So let's say you aren't doing any data analysis today. So you just want to use last year's spend as your forecast and budget for the upcoming year. Now, if we jump ahead to the end of the year, let's say you're actually under budget. So that sounds like it's a good thing. But I would say that that gap is actually a missed opportunity, because throughout the whole year, you had that money allocated towards your cloud, and you couldn't invest it anywhere else. And so if you had a better forecast, you would actually be able to use that money earlier in the year for hiring an engineer or something who can create business value. And so I've outlined a couple of the personas here from my perspective of how I think FinOps should interact with forecasting and data science. So from a finance perspective, they're most interested in the overall budget, and so they'll be looking at cost as a single variable and maybe adding some growth rates to that. And then on the engineering side, they are most interested in asking for budget for next year for new projects, and so they might be making some educated guesses about the resources that they'll need and doing some calculations based on that. And I would say that this falls into the area of better planning, so that if you get a better baseline, you can improve on this area as well. And then for FinOps, I put FinOps and the business together because we kind of share the same goals. And so we are interested in planning for our EDP purchases and our RIs. And so for us, it's going to make sense to have a multivariate model where we factor in all of our cost drivers to get those deeper insights. And so this is what I hope to build up to by the end of today. All right, but before we go into that, we have to talk about the different types of data that exist. So first, we have cross-section data. And this is typically what I think about when I think of data analysis. This is used in surveys and research for causal analysis. So you might have one set of data and you want to compare it to another set of data to see if there's any changes based on a treatment variable. Now, on the other hand, we have time series data. And this data is different because you're actually collecting data sets in an ordered set over time. And so our goal here is to track the patterns in that data. And this is most commonly used in economics and in stock market analysis, as well as business. So for FinOps, we are actually more interested in the time series data. And so that's what we'll focus on today, doing some time series analysis. All right. And so again, before we get into the patterns, we have to build up some foundational knowledge. And so we are going to work on creating a model for our data. And so we want to mathematically capture the dynamics in our data and put that in an equation. And so bringing it back to physics again, we're all familiar with the equation E equals mc squared, right? And so that is actually a model for what Einstein was observing in the real world. And so we are trying to do the same thing for FinOps to create a model for what we see in our cloud costs. So one type of model that we can create is called a linear model. And what that means is that you can add different terms that represent different components, and you can keep adding that to your model until you're satisfied that you've described your time series, which is our data. And so there's 4 different components here. So first we have our trend, and you'll be able to see it up there. But basically, in this data here, this is real cloud cost data, and you can see in general, it has an upward trend, and so that represents one component. And now, within that data, there's also some peaks and troughs, some bumpiness there. That's going to represent our seasonality or our cycles. And then we can't see it on the chart here, but there's always going to be an error component to our model. And so the errors there represent the difference between our model and the explainable part of the underlying data generating process. And so we'll go into more detail later on. There's also some advanced components, such as moving average and autocorrelation. And these are harder to see visually, and so we have to represent those mathematically. And so we'll go into each one of these individually so that hopefully by the end of the talk, you'll be more familiar with all of these. All right, and so I want to bring it back to what we do as FinOps practitioners. So our job is to look at the changes in our cloud costs, why things are going up and down, and communicate that to others. And so in order to be able to communicate that, we have to understand what variation is and what causes that. And so there are 2 types of variation. There is first assignable variation, and this is a type that you can control for. You can assign a cause to it so that you can go investigate and figure out what caused that. Now on the other side, we have random variation, and this is something that we can't control because it's basically just white noise. And so an example of what causes white noise is, let's say you have an engineer who maybe leaves every day sometime between 5 and 5:30, but you never know exactly when they're going to leave. And so we can treat that log off time as a random variable. And so that one's completely random. And an example of that on this slide, we have a chart that shows white noise. And so white noise is completely random. And this is what is actually called a stationary process. Now, stationarity is another important concept in time series analysis, and it basically means that you have a constant mean and constant variance. And so in this white noise chart, you can see that it's pretty constant about that middle point, so you have an equal number above and below that 0 line. And then the variation, in general, has a pretty stable width going across. In contrast, we have the random walk slide or chart, and this one you could see that in the second half of it, there's kind of an upward trend, and sometimes there's bigger spikes than others, and so this one is definitely not stationary. And so we want to make sure that, going back to the errors, those errors, we want that to look more like the white noise than the random walk, because it means that we've accounted for everything in our model. So if there's still some structure in our residuals, then it means that there's something that we're missing in our model that we want to still go and capture. And so the next part of the slide I want to talk about relates to manufacturing. So from a manufacturing process, you have a machine, and it spits out widgets. And you want those to be the same every time because your customers are going to be purchasing those, and they should know what to expect. But they're never going to be exactly the same. There's going to be some variation there. But sometimes there are products that come out with a huge defect. And when that happens, again, that is assignable variation. And so from a manufacturing perspective, they go and figure out what that is and fix it so that the machine is back in control and they're making their products the way they expect. And so they might go in and tighten some screws on the machine or something like that. And so we do the exact same thing for FinOps. We use our optimization best practices to bring all of those processes into control. So theoretically, if you had a workload that you have in one account, you should be able to move that workload over to another account and see the exact same behavior. But that's only true if you are making sure there's no waste in the environment that could interfere with the process that you're trying to analyze. So from FinOps, I have some examples of some stable processes that we might want to start with, because those stable processes are going to be easier for us to model. And so an example would be maybe you have your IT applications. And so those are likely going to stay stable with the number of users. Now we also have our high availability resources. And so those are going to be long running, and they're just waiting for a failover event. So those are super easy to model and forecast as well. But then some other ones that we might want to wait until we have more complex methods would be your R&D accounts. Those are probably going to depend on randomness from whenever people want to test things out. And then your cloud native applications, those are actually designed to be kind of spiky depending on usage. And so those will be more complex to model as well. All right, so we'll start with an example of a simple, stable process that we can model. And again, I'm taking some ideas from manufacturing. So this is called a process control chart, or an XMR chart, which comes from Six Sigma. And basically, there are some equations in the top right-hand corner. And these equations help us to calculate an upper control limit and a lower control limit. And those are going to be the thresholds for our stable process. And you can see those represented in the chart through those red lines. And so as we collect our data, if we happen to find a data point that is either above or below those lines, then we can say that that is likely due to assignable variation, which means we can go investigate that and find a cause and fix that. And so it's basically an anomaly. This is like an anomaly detection tool. Now, everything that happens within those thresholds, we can say that that is due to white noise. So you don't want to spend time asking your team what caused a spike when it's likely not in their control anyway, and it's just due to randomness. So this kind of chart literally helps us filter out the signal from the noise. And then also from a forecasting perspective, if you look at that threshold, you can say for the stable process that you're confident within Six Sigma that this process will stay within that range going forward. And so if that range is okay for you, then you're good. If it's a bit too high, then maybe you want to go and do some optimizations on the actual architecture to bring that back down. All right, so that was a simple example of a straight line. We're now going to do a line with a slope or a curve. And so, again, for this example, I'm using some real cloud data. And this is an example of a performance test. And if we look at just the left-hand side at the bottom there, we can see that it has a general upward trend. And this trend is pretty easy to model. I actually just went into Excel and clicked Add Trend Line to get this one. And there's also an equation at the top. And that's kind of what these trends are based off of. This one looks like the equation of a line. But you can see we have these betas. And when we estimate our model, those betas are actually called parameters. And so we can do this through using your actual data through a process of linear regression to get those estimates. And these types of models can get even more complex, because remember I said they were linear, so you can keep adding different terms. But right now, we'll just focus on the simple one here. And now, something to watch out for is if we look at the second chart, this is that same process, but now that trend is going in the complete opposite direction. And so this is called a structural break, which means the behavior of your process has now fundamentally changed. And so the previous model that you were using is no longer an accurate predictor of that cost. And so if you were to follow that line out over the long term, you'd be completely off. And so what we want to do here is create a new model for our data. So when we do that, I mentioned we use our data to estimate that linear regression. We're only going to include the new data in that new estimate, and we don't want to include any of the stale data in there because that no longer represents the behavior. And so this is where I recommend doing it yourself versus using a tool, because a tool might be able to guess at these structural breaks, but they'll probably be maybe too late, or they won't know exactly where it happened. But because you know your business, you know when people decided to make a change. And so you can pick which data is most relevant to you. So. All right, so we have our first component. And the next two are going to be seasonality and business cycles. And these two kind of go together. So there's a lot of definitions out there, and they differ a little bit, but my preferred definition are that seasonality is going to be something that happens every year, whereas cycles happen over multiple years. But that doesn't really work for FinOps, because we look at data on a daily basis, maybe even hourly, and so I've redefined that a little bit here for us. So I'm going to say that seasonality is generally over fixed time periods, whereas cycles are generally over variable time periods. So we have our peaks and troughs that don't happen at those regular intervals. And I have some examples here. Again, some real cost data from our environments. And so the first one represents our RI purchases. And you can see that these happen at the same day every month. And there's a big spike when that happens. And so this one we can consider to be seasonality because of that fixed time period. And now on the second chart, I called these weekly drops, but this is when teams ramp down their machines on the weekends and then spin them back up. And that kind of depends on usage, when people decide to leave and stop doing some work, so that's not going to be the same every single week. And so that one we can consider a cycle. But there's some judgment that comes into this too. They're very similar. And so again, this is where you might be able to do a better job than some tools, because you can look at the business and figure out if it is closer to a seasonal pattern or a cyclical pattern. And there's some methods that we can use to calculate these, which are going to be your seasonal ARIMA, seasonal indexing, cyclical ARMA, and those are all complicated terms. I'll go into the ARIMA and ARMA equations in the next slide, but we don't have time to go into seasonality too much, so I'll just touch on it a little bit in the next slide. And then some examples for processes in FinOps that might fit with these are going to be if you have end-of-month processes as well, maybe your cost spikes up towards the end of the month, or if you have people who go on vacation in the summer at the end of the year, they might not do as much in their R&D environment, so your cost might go down. So that could be another example. All right, so we've gone over all the simple things. So now we're going to get into some more complex methods. And so when we build our model, you can keep adding those terms, but you don't want to add too many. You only want to add those terms if those structures are in the data. So let's say that you've created a model, and our residuals, which are the difference between our model that we've created and the observed values. So if those residuals still have some structure, like I mentioned, if they don't look like white noise, then we want to go back in and tune the model and use some of these more complex methods to try to pick out more structure in the data. And so a couple of these, they pretty much go together. We have autoregression and moving average. So in that first equation, I have autoregression, which is an AR1 model, and we have our x of t is equal to x of t minus 1. So basically, the intuition for this is that your data today depends on what your data was yesterday. And so for cloud, there we go. You're not going to have just completely random data every day. Nope. You're going to have, nope, there we go. You're going to have ongoing projects and continuations of what you were doing. And so, yeah, your costs today aren't going to be just completely higher than they were yesterday. You're going to be influenced by the data points either a day before or 2 days before, depending on what was happening. And so that's what these models are trying to describe. So similarly, we have the moving average process, which is where your data point actually depends on the previous error in your model, which is the W of t minus 1. And now you can put these together because they are linear and come up with a single equation. And so that's what that next equation is. And this one is called ARIMA. It would be called ARMA if we have just the AR and MA, but there's also something called the integrated difference, which I also don't have time to go into. But if you're interested, you could just know that the differenced data contains an ARMA structure. And so when we put it together in this model, we have our ARIMA 1, 0, 1. 1 for the AR, 0 for the integrated difference because we didn't consider that, and then 1 at the end, again, for the moving average. And I also want to mention that those numbers can get higher as well if you want to consider even further lags in your data. So for example, if we wanted to model in AR3, so if your data was influenced by 3 days back, then our equation would look like x of t is a function of x of t minus 1, t minus 2, t minus 3, and so on. So they do get a lot more complex, but it helps us to model more complex structures within our data to try to get it more accurate. Okay. So everything we've done so far has just been a single variable, which is cost over time. But as FinOps practitioners, we actually have access to a ton of data out there. We have our usage data. We might have some, I guess, leading indicators like sales or lagging indicators like the amount of data processed. And if we want to include all of that in our model, we actually have to go from a univariate model to a multivariate model. And one method that we can use to do that is called vector autoregression, or VAR for short. And you can see that this equation here, it looks pretty much the same as all the other equations we've gone through. This is also going to depend on previous lags of itself. But in this case, the coefficient on our variable, the x of t minus 1, that is going to be a matrix, whereas everything else in this equation is a vector. And that's where we get the vector autoregression. And the reason for that is because we actually have a system of equations now to represent all of the different variables that we want to consider in our model. And so the data that actually goes into these types of models is called panel data. Now, remember back to the beginning where I talked about the difference between cross-section data and time series data? Well, in this case, we are going to bring in the cross-section data, and we're going to put them together. And panel data is basically just that cross-section data over time. And so this is where it becomes really powerful because now we can model the dynamics between some of the cost drivers and your actual resulting cost trend. So. All right, so we've done all of that work, and what we've come up with is a model. And I've mentioned that for me, one of my goals is forecasting, but we don't actually have a forecast yet. So what are some things that we can do with just a model? Well, we can do some historical analysis. We can pick out those anomalies that we saw. We can also do some root cause analysis to figure out what caused those if we have a multivariate model. And we can do counterfactuals, which are what-if analyses. So we can go back and plug in maybe what our sales were and what we think our cost would be if our sales were maybe 20% higher or something like that. And so those are the different types of deeper insights that you can get from this type of data. But now if we want to turn this into a forecast, what we have to do is we take our model and we use our actual data and we plug that into our model. And when we do that, we get a point forecast that gives us the next step ahead. And that point forecast is going to have an error attached to it because you're never going to get it exactly correct. And so you keep doing that and you keep plugging in the next value into your equation and you iterate over that until you get to your desired time horizon. And so time horizon is a choice you have to make at the beginning of doing your forecast so that you know how far out you want to have your forecast. And just know that your forecasts are going to be more accurate in the short term versus the long term. Now, we also have confidence intervals. And so if you look at this chart, that solid blue line represents actual cost data versus the fuzzy line, which represents a forecast. And you can see that your forecast is more likely to fall where that line is darkest. And there's some bands of thresholds that go around that where it's less likely, but it's still possible that your forecast could end up in there. And so those are your confidence intervals. If you want to be more confident, then that threshold has to increase. Now we also have the compounding of errors. And so again, if you look at this chart, when we're closer to the actual data, those thresholds are a lot smaller. But when you get further out, they get a lot bigger, which means that our uncertainty about the forecast also increases. And we get the compounding of errors, like I mentioned, when you plug it into your equation and you keep iterating over that. Each term has that error attached to it, so you're propagating those errors through, and every time they're getting a lot bigger. And so because of that, we actually want to iterate on our model over time so that we can keep it within the accuracy that we want to get. So that means that rolling forecasts, which are already useful for FinOps, we want to keep doing that with our model and adjusting it so that we can be as accurate as possible. Okay, so now that we have our model, is it any good? So how do we actually get the accuracy that we want out of it? So we can't get rid of that error term, and that error term is actually represented in this chart. So we have our data points as the blue diamonds, our model as the green line, and then the residuals, the errors that we want to track, are those purple bars. And so some methods for actually calculating that are going to be the root mean square error, which tries to get a measurement for the magnitude of all of those errors. And so if you have multiple models, you can compare that metric, and you would want to pick the model that has the lowest RMSE because that means your model is going to be more accurate. Now for time series specifically, there are some more likelihood-based heuristics. Okay, yeah, so the AIC and the BIC, those are more commonly used for time series specifically, whereas the RMSE is used more for all of the other types of analyses that can happen in data science. And so typically you want those to be lower because, again, it measures how accurate your model is going to be, but sometimes they don't always match up. And so if you have models that provide the same metrics, but you don't know which one to pick, always go with the simpler model, because there is a principle within data science, which is the parsimony principle. And what that means is that we don't want to overfit our models, because if we add too many terms and try to get a perfect match, we'll be able to perfectly predict the past at the expense of being able to accurately predict the future, because you need that flexibility. And so also another benefit of having these simpler models is that you'll be able to understand them better, and thus you'll be able to explain them to other people better as well. So, all right, so I mentioned that time horizon is an important factor. And so when you're creating your models, you want to make sure you're considering the granularity of that time horizon as well. And so different models are going to work better in the short term versus the long term, and you're going to get more accurate forecast in the short term. And so let's say you want to forecast out 3 years from now. You probably don't want to use your daily data points, because that's going to take a lot of iterations to get to that 3-year mark. And so your errors are going to compound a lot. But if we use monthly data, you're going to have fewer data points, and so you're probably going to get a more accurate forecast or model of your data. And so that's due to the aggregation effects of bringing all those data points together. And so this is an important consideration if you're going to share these models with leadership, because they might rely on those for business decisions that they're going to make. And so you need to understand the impact of the choices that you make when you create these models, and how that's going to impact the decisions that other people will make as a result of this. And so basically, for FinOps, for me, it's about business value. And so if we know that our forecasts aren't as accurate as they could be, then there is actually a cost to the business of not having all of that knowledge. And so I do have an example here in the chart. So this is a scenario where maybe you're comparing using run rate versus a more complex forecast that can get you that accurate data. So let's say you're trending under budget, and your run rate doesn't really tell you that, because it just tells you where you are today. So it doesn't know where you're going to be at the end of the year. So if you know that ahead of time through a better forecast, then the business can decide that, okay, we're under budget, maybe we can allocate more of that spend. Remember that gap I talked about in the beginning? They can proactively apply that to something else and get some business value out of it and still meet budget. But if they didn't have that information, then they might miss time to market by not having people work on new things. Now, in the other scenario, let's say you're actually trending over budget, but your run rate, again, doesn't tell you about what the future is going to be, but your forecast can. Now you can actually decide that maybe, since we're going to be over budget, maybe we invest less in R&D, or maybe you ask for more budget, so that either way, at the end of the year, you meet that budget. But if you don't have that forecast, you won't know until it's too late. You'll get to the end of the year and realize that you're already over budget. And so in both of these scenarios, the red areas here, those actually have a cost to the business that you might not be measuring right now. So you might have some forecasts that you're using and those work for you, but I would still recommend tracking accuracy as a KPI so that you can determine if your accuracy is too big to where it's actually having an impact and a cost to the business. Okay, so we've made it through all of the math, and we've done our modeling. Now I want to talk about what my team is doing today. So I'm lucky that I work at a data company, and so I have access to a data science team, and so I've been partnering with them to collect our large cloud data sets. And we decided to go with a multivariate model from the start. And so the data science team, they are experts at making sure our data is accurate, prepped, cleaned, and that everything matches up in time. And now what we're able to do is tune our model to be able to answer some of our most critical business questions with more accuracy as well as more granularity. And so what's really cool about this little picture here is that previously we were looking at our infrastructure and mapping that out and figuring out the patterns there and translating that back to our costs. But now we have access to more of that data, and we're integrating that together so that we can actually look at the front end, which I consider to be kind of the business value side, and we can see what that type of usage triggers on the back end, and then connect that back to cost so that we have a direct path from our front end usage to our cost so we can see what the impacts are to the business if our user behavior changes. And so that's super powerful. We didn't have that before, and so it's really exciting for me to be able to use those insights and share those with business leaders. All right, so here are some recap steps. I'm not going to go into detail here because we went through all of these, but I put this in order of what I would do if you wanted to create your own forecast. And I would say the most important thing here is to set a goal for yourself and start tracking those KPIs so that you know when your goal has changed or when you need to set a different goal or actually invest in more forecasting. All right. Now, how can you actually start doing this for your FinOps practice? So I would say try it out yourself. I mentioned some of the simple examples at the beginning with the stable processes. Those have just one equation, and so you can map any sort of metric over that and figure out if you have any anomalies. So I would definitely start there. Then I would also recommend, if you don't have a full data science team, you can connect with some internal teams. Maybe on the business side, they might have like a business analyst who has some data science experience, and so they can help you out. You can build a partnership there. And then lastly, if you are expanding your FinOps team, I would say hire someone who has some data science experience, because then you get a person who is dedicated to you, and that's always useful. Now, I also have some caveats. So these are things to watch out for. I mentioned some of them. So we talked about overfitting and picking the time horizon. But also, you want to make sure that you're not treating your model as the truth. So there's a lot of judgment and art that goes into it. You get to pick a lot of the metrics that you want to measure, and you get to decide if something is more accurate than something else, and it works for your use case. And so there's multiple different models you can use. And so when you are sharing your models with leadership, make sure that they know that this is one data point that they could consider in all of their analysis, and that this can't answer their questions for them, but it can help them to make better decisions. And so I guess a little bit of a story. I've collected some ideas from different scenarios that can happen really often. So let's say you have a business strategy right now, which is to maybe launch a product in another region. And you've done all your forecasting, and you have a really accurate model. And so you know that this workload, when you put it in this other region, you know exactly how it's going to behave. So you go ahead and you buy like a 3-year ROI on that. And if everything stayed the same, that'd be great. You'd be perfect. You'd be perfectly optimized for that. You won't have committed to too much of the ROI or too little. Now, let's say that unfortunately a natural disaster occurs in that region, and now they're not ready for your product. So now your business shifts strategy, and they're going to delay the launch. And so what happens to that commitment that's over there? You've already committed to that amount. And your forecast couldn't tell you that that was going to happen. Your forecast was accurate. But there's so many other macroeconomic or externalities that kind of factor into this. And so you just have to be aware of that the models can't tell you everything. And so that's where, if you do want to get more complicated, you could probably add another term for risk of macroeconomic factors, but that's for another talk. So I don't want to end on like a sad note. So I would say by investing time in these models, you can get more accurate and you can get more insights, and people will understand the uncertainty that goes into all these decisions so that they can make better decisions as well. And hopefully with these deeper insights, going back to the beginning, hopefully you'll be able to answer some of those more why questions, and I encourage you to keep digging into the why as well so that you can pick out some of those externalities. So before I end, I want to just talk about some of the resources that I've used, because I think it'll be useful. If you guys want to get really deep into this, the first two go really heavy on the math. The second one is more of a business, or I guess the third one down, that's more of a business-focused one, so it will actually take you through step by step if you're starting from scratch, and it'll provide all the business context. It's also, that one's really big because it does go through every step. The fourth one down, this is one I would recommend actually starting with if you want to get an intuition for the statistics. This one is about 100 pages, and it goes over mostly just the anomaly detection stable process that I mentioned at the beginning. And that one is the one that I first started with, and so it got me really excited about everything that we could do with data. And then also, if you don't want to read, if you want to just watch people, I put some courses down there as well, the Coursera and DataCamp courses. Some of the people are authors of these books, and so you'll get information presented by the people who are basically the source. So thank you, everybody. Come find me later if you want to talk more about data science, and yeah, that's it. Oh, questions?
Aren't you glad she did this for you? So you don't have to do it. She figured it out. We do have a little bit of time for Q&A. Is that okay?
Yes.
Anybody have a question? There we go.
Okay. So when you first got started with this, were your budgets actually modeled accurately, or how did you handle the conversation of having better forecasts that were very much at odds with the budget? Because we've been through that.
Yeah. So I would say that like finance has a threshold where they're tracking budget, and so if things are too high or too low, even if it's too low and they can't explain it, then that's an issue. And so there is a threshold that we have, and so by having more accurate forecasts, we can make sure that it always falls within that threshold, and if it doesn't, then we have to go back and fix something. So.
Is that conversation easier with your models?
Is it easier? Well, I mean, it still involves going back to the engineer. So you might be able to pick out those issues ahead of time to be able to get the story rather than seeing it after the fact and then trying to figure out what happens. So I would say, yeah, it gives more insight proactively.
Thank you for the presentation. 2 questions for you. One is, are there any linkages with focus based on what you've shared here? That's one. Second, is there any tool that you would recommend, or set of tools that you would recommend that do this out of the box, like that can create like a equation or tell us, what is the kind of thought process that we can use or work with so that we don't have to go back, look at the tool and look in the data and then find out how I fit it. Because that seems a lot of work.
Yes, definitely. So for the first question, for focus, so I didn't do anything specific with that, but if you collect all of your data with the focus framework in mind, then you can just use that data already condensed into one data set and then build models off of that. So that's what I would recommend. And then for the second question, so some other tools, I forgot to mention it, but some of the charts when I was talking about the white noise and the random walk, I can even go back to those if you wanted to see, because I didn't let people take pictures of this. But basically, these charts were created in the R programming language, And that is free and open source. It's also popular among economists and statisticians because it makes it really easy to plot these and get those calculations. And I did put some little snippets of code if you wanted to try it out later. I actually would recommend doing that because it shows how easy it is to start some of these things. And it doesn't really do that for you automatically. You still have to know what you're doing to build that out. So if you wanted something, I mean, I do recommend, I'm trying to get away from just using something automated, and I want people to actually like dive in and dig into all of the different things that you can do, because you can really customize it. But I know there's like AI tools out there, like Profit. Profit is good for a single metric. And so if you know all of this, you'll have more insight into what goes into that, so that if you know if you get a good result or if you want to change something, so you know how it works on the back end. I would say, yeah, for a multivariate model, I don't know if I have a tool out there for you, but through R, there are some software packages that will help you to like it'll do the regression for you, so you'll get a model. You'll just have to know what inputs to provide. Oh, I guess it was me. Okay.
Yeah. Over here, this side. How do you determine what the optimal granularity you want to use for your forecast? I mean, do you want to maybe forecast your entire cloud infrastructure costs, or by provider, by service? Like, how do you determine how granular you want to go?
Yeah, definitely. If you can, I would split it out, because I mentioned there are some processes that are going to be more stable and some that are going to be more random. And so you could have separate models for all of that. You could also, if you have a multivariate model, you can have each one of those as a separate linear regression that goes into it. So you can also see if one of those more random processes has an impact on one of the more stable processes. So you can get as granular as you want. You don't have to, but it probably would be harder to model something that has both like stable and random stuff in it. So yeah, that's the granularity about like the different types of services and things. For like the daily granularity and all of that stuff, I would probably, yeah, if you're doing short-term forecasts, you could probably get really granular, but long-term forecasts for the actual time horizon, you want to probably aggregate that data. So, I mean, it's up to you, so, yeah.
Yeah, I don't really have a question. I have a statement for the lady. We have an out-of-the-box forecasting solution that's multivariate and also available in Alteryx. So let's talk.
Yeah. We got one more question this way.
All right, I'll try to make this a question. It strikes me that your multivariate analysis veers into the area of unit economics in a fashion.
Yes.
Can you speak a little bit about how getting a handle on unit economics actually fits this? Because I see that as an important element of forecasting.
Yes, definitely. And I didn't mention that before, but with the stable processes example, you probably want your unit costs to be stable because they represent something about your business value. And so if something's changing with your unit costs, you want to be able to pick that out. On the multivariate side, the factors that go into calculating your unit cost, you can actually have those as separate regressions, so you can track those cost drivers over time. And then through this analysis, you can see the impact on the change in one cost driver and what that impact has on your unit cost. And you can see the dynamics between that cost driver and a different cost driver, and you can track that over time. So I would say that your unit cost becomes almost like its own single time series that you can track and have all the different components in it that leads up to it. And let's see. So yeah, I guess the better part about this is you don't have to necessarily go calculate your unit cost every single time. You can kind of track it over time and measure those dynamics. And through that model, you could actually forecast out your unit economics as well, so you can catch things ahead of time if they're going to have an impact on the business. So.
I don't believe my college statistics professor explained it
Thank you.
Thanks for watching. Check out more FinOps X 2024 content on our YouTube channel on the 2024 playlist. Support our channel by liking, subscribing, clicking the notification bell, and by leaving comments and questions for our speakers. We appreciate your support.